All right, so this is the last time that you're going to hear from me in this last session. I'm going to talk a little bit about model assessment, which is something that we haven't talked about a whole lot in this workshop. And we are going to see that it is not always rainbows and sunshine and positive things. Sometimes we do have problems with our models. So specifically, I'm going to talk about that, what to do after you've run your model and you want to know a little bit more about goodness of fit. So we're going to talk about Markov chains, which we mentioned yesterday. It's kind of scary. And some diagnostics like R-hat and effective sample size, as well as best practices for correcting divergent transitions. These are some words that you may have heard of so far, but if not, we are going to talk about them. Basically, I'm going to try to take a topic that is quite complex, and I'm going to simplify it for you, like I was trying to explain it to my daughter or something. That's going to be the goal. So the purpose of this session is to help you build intuition about how the sampling process works and to know when your model is poor, when your model fails. And luckily, BRMS is actually quite verbose in that sense. It will let you know if things are not going right. So if you have young children or you're fans of Disney Junior, you might recognize this person on the screen. This is Mita, the royal detective. And if not, Mita is the star of my daughter's favorite mystery cartoon. And she's a brave and resourceful royal detective in a fictional kingdom called Jaipur. And she travels around this kingdom and she solves mysteries. So this is similar to what we do, especially at first, right, when we're building and assessing models. So the plan here is that we're going to be like Mita and we're going to solve some Bayesian mysteries. And we're going to get a good introduction to what the topic is, but obviously it can't be exhaustive. And at the end, I'm going to give you some more references for further reading. And I do also just want to point out, me specifically, this is like my year 5 for me on my Bayesian journey, I guess you could say. And a lot of these things that we're trying to teach you in 2 days and 4-hour sessions are things that took me years to get my head around. So it is completely normal if a lot of this is painful or if a lot of this doesn't make sense yet. The idea is to just slowly build up intuition about these things over time. And then it sounds like a lie, but eventually it just becomes a little bit more intuitive. It can be a slow process, but that's the way it works for most of us. So we hinted before that Bayesian regression involves complicated sampling algorithms and that these sampling algorithms help us to approximate a posterior distribution, right? You may have heard about one specific class of these algorithms before. They're called Markov chain Monte Carlo methods. But if you haven't, that's totally fine. We're going to break this down a bit and simplify. So what is a Markov chain Monte Carlo algorithm? What it does is, and this is what happens under the hood when we fit a model in BRMS using the BRM function, we actually, by default, we're running multiple Markov chains to do sampling. The default is 4. The chains sample the parameter space. And I'm going to talk a little bit more about this in a bit. In fact, over the last 2 days, we've been saying parameter space a lot. We're going to build intuition about what that is as well, right? So these chains individually sample the parameter space. And then what we can do is actually assess these chains to get an idea of how well the model converged for us, okay? And if the sampling procedure is not optimal, then we can inspect the chains and we can have an idea of what went wrong, what we can do. And we're going to look at some of the diagnostics that BRMS gives us by default. So the main way that we do this is by looking at what are called trace plots. You may have seen these before. They're kind of crazy at first, but once with a bit of an explanation, it should make a bit more sense. What we're seeing on the vertical axis is values for the parameter that we're a parameter of interest. In this case, we're looking at the intercept, but it could be any of the parameters that we fit in a model, right? On the horizontal axis, we have the iteration number of the sampling procedure. So we can see it starts at 0 and then it goes to, in this case, 1,000. This is what happens when we actually run the model and we see the lines go up really fast. It looks like the Matrix and we feel like hackers. This is the iteration process, but we're looking at the time course, I guess you could say, on the horizontal axis. So this is an example of what we would call a good model. These are healthy chains. In other words, we would conclude that the algorithm worked here. We say that the chains have mixed well, right? If we look from left to right, what we see, we can describe this as a hairy caterpillar. This is kind of the scientific jargon that people use when they talk about chains. So when we inspect our chains, this is what we want. Now it's hard to tell, but there are 4 different lines here. They just go up and down randomly, very fast. And the different colors of blue, the different shades of blue represent each of the 4 chains, all right? So this is also a healthy chain, a hairy caterpillar. I'm going to give you examples of what it looks like, a good example that we just saw, and also what happens when it fails, when we have a very poor fit. So that would be this plot, for example. If the sampling process does not work properly, we might see something that looks more like this. If you follow any given line horizontally from left to right, you'll notice that they do not sample all of the parameter space vertically like we saw in the previous plot. There's not a lot of random up and down movement. In other words, there's no hairy caterpillar. And in this case, we would conclude that the chains have not mixed well. Now, determining if your trace plot looks like a hairy caterpillar is not precisely an exact science, but there are some diagnostics that BRMS gives us by default that will tell us information about our chain's performance. Those ones are specifically R hat, and then there were two estimates of effective sample size. So we're going to talk a little bit about each of these. You probably noticed over the course of the last 2 days that we see these in the summary on the far right-hand columns. Some of you asked about these, and we said, don't worry, it's coming. Well, here it is. So we're going to look at the output of a simple model, right? The two diagnostics that we're talking about are in this. This is the same model that we fit the first day with articulation rate as a function of attitude. Now there it is right there. We can see the model as Timo showed us. This is the formula that we had to. What I want to do right now is actually call your attention to the samples row right here. All right, this whole thing here. By default, I mentioned this before, by default, the model is going to run 4 different Markov chains, right? Each one is going to give us 2,000 iterations, 2,000 samples, but we're going to take 1,000 of those and we're just going to get rid of them because we're going to consider that warm up. The algorithm has to get going when it starts to sample, and this just it's warmed up, and then once it's warmed up and it's humming, we throw those out. So what happens is we end up with a total of 4,000 because we have 2,000 iterations on 4 chains, half of which are thrown away. So that's a total of 4,000. That's why by default, when we get a posterior from any of the models that we fit, we have 4,000 rows in our data frame that we extract from that. Now, I'd like to call your attention to this part of the table. You have already noticed that these 3 columns on the right-hand side, again, this is R hat, bulk effective sample size, and tail effective sample size. So what is this all about? R hat is a convergence diagnostic. It compares estimates between and within the 4 chains that we fit. I'm simplifying here roughly, but you'll get an idea. The key thing that you need to remember is that this value should not be greater than 1.01. No, less is better, right around 1. If it's not in that range, if it is higher than that, then that is a sign that the chains did not mix well. All right. In other words, between and within chain estimates don't agree with each other. That's indicating a problem. In this case, we can see that the R hat values are all right around 1 for the population level parameters, and also for the sigma, the family parameter, a little bit lower. With regard to effective sample size, this metric tells us about the number of independent draws that have the same amount of information as the dependent sample obtained from the Markov chain algorithm. Now, that is a lot to unpack, and if you don't understand that completely, that's totally fine. I'm going to give you some rules of thumb about what we need to know about these as we go along. The general rule is they should be higher. The higher, the better, right? Specifically, for bulk effective sample size, you should have 100 times the number of chains that you have. So in our case, we have 4 chains. 4 times 100 is 400. We can see that this is well above 400. The maximum possibility would be the number of iterations that you have, for example, 4,000 in this case. The tail effective sample size is doing the same procedure, but it's pulling from the tails. So this one is naturally lower, but in this case, this is a healthy model. This is pretty good diagnostic. Okay. Now, again, we're going to look at the same model before that was really bad. When we looked at the trace plot, there was no hairy caterpillar. And we're going to see what the output of that model looks like. Just to give more information, it was hard to make that really bad model, but I ended up just giving crazy priors that didn't make any sense with articulation rate data, for example. And then eventually it made it really hard for the model to converge. You couldn't sample the parameter space well. So again, this is the poor model. We'll notice that if we look at R hat, the values are much higher than 1.01, right? And the effective sample size are too low, right? They are much lower than 100 times the 4 chains that we have. They're lower than 400 in both cases for bulk and the tail. Now, you will also notice if you have a model that is bad like this, that BRMS will give you a warning, usually something that looks a bit like this that you see here. Note specifically that it gives us caution. It tells us to take caution when analyzing the results, and it also gives us helpful solutions. I think this is quite good because sometimes with other warnings, for example, in LME4, it'll tell you that the model didn't converge or that it's singular or something like that, but it won't really tell you what that means in terms of interpreting the output that it gives you or what to do to fix it. So in this case, it does give us a suggestion. It says, first of all, that we could run more iterations on each chain. By default, it was running 2000, but we could increase that. And it also says to take a look at your priors. And that was what the problem was here, that I purposely changed the priors to something really, really poor so that the model wouldn't converge, right? Now, the way that we could do this, obviously, we specify our priors in a different object. So we could relook, rethink, and go back to the drawing board on our priors. And we could also just change the amount of iterations of the sample. So by default, it's 2000. We could change it to 4000 or 10,000. Something that's a lot higher. In this case, I increased the iterations and I also increased the warm-up, the amount of samples that are used for warm-up. Now, you'll also notice that there's another warning right down here in part 2. And in this case, it talks about divergent transitions. It says, be careful, there are 497 divergent transitions in this case. BRMS also gives us a good solution for combating this problem. It says that we should increase adapt delta. All right, so this is great. We already know what the solution is, but we don't really know what the problem is yet. We don't know what divergent transitions are. So I'm going to spend a little bit of time now trying to build some intuition about what divergent transitions are. But in order to do that, we have to talk about parameter space a bit more. So what is parameter space? You've probably noticed we've been saying that a lot over the last 2 days, and it may not be completely intuitive. So let's consider some made up data, just a fictional data set where we're looking at y as a function of x, totally informative. And imagine that both of these variables are continuous, right? We could plot them in a scatter plot like the one you see here. This would be what we call the data space, right? The outcomes or the two variables that we're looking at are on the actual scale that the data were measured on, right? We can fit a line through this data, just a standard regression, and look at the intercept and the slope. Now let's look at another plot. We have the data space still here on the left-hand side, but on the right-hand side, we're going to look at the intercept in the slope and the slope in a scatter plot, right? This is what we call the parameter space, the possible values that the parameters can take, right, that are related to the model that we fit in the data space. So this allows us to compare the data space with the parameter space in an interactive way, okay? Oh. Reload. Sorry, I didn't notice that it didn't come up. Let me take a second here. Okay, it reloads. There we go. There we go. I'm going to repeat that just in case you didn't catch what I was looking at while I said that. So on the left-hand side, we have the data space like we saw in the previous plot. On the right-hand side, we're looking at the intercept and the slope from this red line. It's represented by the red dot. So we have the intercept on the y-axis and the slope on the x-axis. Now, we can move around in the parameter space by increasing the intercept, for example. And we'll notice that the line that we have fit over here moves up as the intercept moves up, and the red dot also moved up in the parameter space. We could also decrease this. We see the plot moves down and the line moves down correspondingly, right? We could also play with the slope, right? We could increase the slope, which would make the line more inclined, and the red dot moves further to the right. We could decrease the slope, and we'll see how this moves around. Likewise, okay? So when we fit these models, we have a specific parameter space. This is a very, very simple example where we're just fitting intercept and the slope, right? This is a very simple parameter space, but we are fitting other models that have many parameters, like the hierarchical model that we just fit with TIMO, right? What the model is doing under the hood is it's taking this parameter space and it's sampling it. We could think of these limits, these extensions, could be, for example, the limits on our priors, right? We tell the model, don't look for something in the intercept way up here because we know something about pitch or whatever we're measuring. We say, we know way up here isn't interesting. We're more interested in this region down here. That's what we do when we set priors. We say, focus on this parameter space rather than like the whole page here, to continue with the example. All right. So we can do that. We could also think about this in 3 dimensions. I showed this plot the other day as well. And this is a similar idea, right? Whenever we sample from the posterior, right, we start building up samples in a similar area, right? And as those samples build up, we think about the distribution is getting larger if we're thinking about this in 3 dimensions. So again, the very light colored values here would represent a very high mountain, like if we were flying over the top. I mentioned that we could also look at this in 3 dimensions, right, to help understand what this looks like. So now I'm going to show you with the simulation how the sampling procedure actually works with BRMS by default. This idea of looking at the parameter space in 3 dimensions is helpful, but because of the math that what's really going under the hood, it's actually slightly different. Just pretend that it's flipped upside down like a bowl, okay? So instead of being a mountain, just pretend it's a bowl. Same shape, but just upside down, right? And I'm gonna show you a web application that looks like this, where we're gonna be looking at this hypothetical parameter space, right? We can imagine that the vertical axis is the intercept from what we were just looking at before, and the horizontal axis is the slope of the parameters that we're estimating. And in this case, the blue circle is, and the gradient at the center represents the depth of our bowl in 3 dimensions, okay? So to understand how the sampling works, let's just pretend that our bowl is a frictionless surface and that we don't know its exact shape. We know it's bowl-like, but maybe there's a bump, maybe there's certain tiny little hills, whatever. We don't know the topography, right? And what we're gonna try to do is figure out what the surface looks like, right? That's what we're doing when we're taking samples. So how are we gonna do that? Let's survey it. We're geographers or map makers or whatever, people that do that kind of stuff. And we're gonna survey this space, the 3-dimensional space. Now, the way that the algorithm does this in BRMS, it's called the Hamiltonian Monte Carlo algorithm, is it's like we placed a marble in this bowl and we just flicked it, right? It's a frictionless surface, so it's just gonna move around in this space. And what we're gonna do is we're gonna keep track of everywhere it goes until it starts to turn around and stops. And we're gonna start there and we're gonna flick it again. And we're just gonna keep repeating this until we've mapped out the entire parameter space. If it's helpful, I think of it like this, right? Have you guys seen these before where you can throw a coin in and it moves around? So you can think of the path of the coin here is what we're using to track the parameter space, but we're taking notes of all of this, okay? So the way this actually happens, I'm gonna run the simulation now, is we're looking at this. I'm gonna just run a couple and go ahead and watch what happens. Hope that you can see this okay. You can see there's each flick of the coin. It goes around in the parameter space and it's taking note of what's going on. In fact, I'm going to slow this down. Each flick is what's called a proposal. And we're keeping track of where it goes, where it stops, and we're marking it down. And as we mark it down, we're keeping track of the intercept possibilities and the slope possibilities. And this is what eventually becomes our posterior distribution. Now, imagine whenever we fit a model, we see that in the console where it goes really fast, this is what's going on, but imagine it being really fast, right? So what happens is we're doing this, we tell the model by default to do this with 4 marbles, 4 flicks at a time, and to do it 2,000 times until we get a posterior of around 4,000 samples. And it gives us, over time, you'll see this, it gives us an approximation of what the parameter space looks like, okay? Now, going back to divergent transitions, which was the whole motivation for talking about this, imagine that we're walking down in this bowl, right? We don't know the exact topography of the bowl, but we're walking down in it as we're doing our survey. And maybe since it's steep, or it could be steep, imagine that we're taking steps that are way too long, right? Our stride is too long. We could fall. It could make it difficult to go downhill. That's the equivalent of this movement, this flick that we see in the parameter space. Imagine when it starts to turn, that you fell off the track, right? Think of this as like a roller coaster and it turns, but your cart keeps going, right? That's what's called a divergent transition. When the turn happens in the parameter space and the algorithm isn't really tuned well enough to keep track of that, and you fall off the rails on your roller coaster. So what the suggestion told us to do was to increase adapt delta. What that does conceptually is tell our little marble to take smaller steps. So imagine you're running down this hill again, instead of taking long strides, you start taking baby steps, right? Now the trade-off is if you're taking smaller steps, you're being less efficient. It might take you longer to get to the bottom of the hill. The same thing happens when you increase adapt delta with your model. It might take longer to sample the entire parameter space. But this is indeed more or less what's going on. Okay, actually, I'll stop that and move along. Okay, so the trade-off of doing this is that your model will be slower. I mentioned that the way you actually do this in your code, right? You'll notice that I highlighted here a line, excuse me, right there. where the argument is, well, let me have it again. The argument is control. And inside of a list, we can put some other arguments. In this case, we put adapt delta, and then we increase the value. By default, BRMS puts it at 0.8, which is, I guess, maybe a decent sized stride. We increase it to 0.99 and saying we're taking smaller steps to explore the space. So 9 times out of 10, if you have divergent transitions, you can change the stride of your step, and that will make it the sampling process more efficient. A lot of times you also have to critically think about, the likelihood of the generative model that you're fitting, and also the priors that you have established. Usually the problem lies within one of those 3 things, okay? Now, this is a huge simplification of what actually happens, but I find it to be quite useful, at least to build intuition. But obviously, as I mentioned before, when we actually do this with a hierarchical model, like we just fit with Timo, that's a high dimensional space because there are a lot of parameters. I think there was like I don't know, 10 or maybe more. It's not uncommon to fit models that have hundreds of parameters, and some crazy models can even have thousands, right? So as humans, we're not capable of imagining what that parameter space looks like, right? But when we have just 2 or maybe 3 parameters, we can kind of think about what that looks like a little bit. So this is more or less what is going on. Now, there are more, I guess you could call this like starting points for getting more information about how this works. So if you're more interested in Markov chains, for example, I have linked a couple of articles that are quite good for those. There's more on RHAT and effective sample size. The STAN documentation is actually really fantastic when it comes to explaining the warnings that STAN gives you. So you might get a different type of sampling warning, and it'll give you a link to what you need to know and what you can do to fix it. This is a lot different from warnings you might get from other packages. And then I gave a couple more articles here at the bottom that are more about the specific algorithm, the Hamiltonian Monte Carlo no U-turn sampler. So if you are interested in these things, which I would anticipate that most people probably aren't, at least not in the beginning, these are accessible resources to start checking those out. And I think that for most people, as you get more interested and you get more experience fitting Bayesian models, you start to become more interested in these things. So with that, I'm going to leave you with a quote that I like from the Statistical Rethinking book. Actually, this was from the videos that Richard McElrath has online, which for me, I think is a great summary of what doing Bayesian statistics is all about. Now it says, we put a tiny sliver of scientific information, that would be our weekly informative priors, into the model, and then we bet on things that can happen a large number of ways. And what it means by that is looking at the things that are the most plausible in the posterior distribution. And that is the end of this session. Thank you once again for your attention. I don't think you'll be hearing much more from me after this one.